Welcome back. Let's do another curve sketching example. So let's say that we have f of x is x squared divided by x minus 3. So the first step would be analyzing the function f, which means I need to know the domain of the function first. And clearly the domain is everything but 3. So it is the interval from negative infinity to 3, union 3 to infinity. We want to find the x-intercept, so these are the points where the graph of f crosses the x-axis, where y is 0, which means y is 0 means the function value is 0. So we want to figure out where the value of the function f is 0. So f is 0 when this fraction is 0, but that means that the numerator is 0, and that's when x is 0. So 0, 0 is the x-intercept. Y-intercept, y-intercept would be the point. So 0, 0 will also be an y-intercept, clearly, because this is also a point on the y-axis. So y-intercepts are the points where the graph of f crosses the y-axis. So that means where x is 0. And when x is 0, clearly f of 0 is 0. So y-intercept is also that. Horizontal asymptote. So as do we have any? Well, what's the limit of f as x goes to infinity or negative infinity? Well, again, the numerator and the denominator, they are powers of x, so the limit will be determined by the dominant terms here. So the dominant term on the numerator is x squared, the dominant term in the denominator is x. So what's the limit of that? Well, x squared divided by x is just x. So as x goes to infinity, that's going to go to infinity. If I look at the limit at negative infinity, we're just going to get negative infinity. In any case, we're not getting a finite number here, so that means there are no there is no horizontal asymptote for this function. Vertical asymptotes. Okay, let's first look at the oblique asymptote. Notice that this rational function, the numerator has a higher degree than the denominator. So if we divide the numerator by the denominator, then by using polynomial division, we can express f of x as x plus 3 plus 9 over x minus 3. That is, if I divide x squared by x minus 3 using polynomial division, then the quotient, this would be the quotient x plus 3, and the remainder would be 9. And then we can write the function f in this way. So the y is equal to x plus 3 is the oblique asymptote for this function. Now, here's what it means. Notice that when x goes to infinity, then this term here almost goes to 0, right? So when x is big, this is almost 0, and the value of the function is pretty close to x plus 3. So as x gets bigger and bigger, it means that the graph of f is getting closer and closer to the oblique asymptote line. Now, same thing for when x goes to negative infinity. When x goes to negative infinity, notice that this term again goes to 0. So the value of the function gets closer and closer to the x plus 3. So when x goes to negative infinity, the graph of f is getting closer and closer to the oblique asymptote line as well. All right, so vertical asymptote would be when x is equal to 3. That's where the denominator is 0, but the numerator isn't. And we can also check the limit at 3 on the right side of 3. As x goes to 3 from the right, the numerator goes to 9, and the denominator goes to 0 and when x goes to 3. But it is going to 0 from the positive side. That is, notice that when x is going to 3 from the right, it means x is going to 3 and x is bigger than 3, and so x minus 3 would be positive and getting closer and closer to 0. So that's indicated by this. So when the numerator is becoming like a constant and the denominator is getting closer and closer to 0 but positive, then the ratio will go to positive infinity. And if you look at the limit as x going to 3 from the left, we are going to get negative infinity here. So that's our vertical asymptote. Next, we need to find out where f is positive and negative. Notice that the numerator is always positive, or at least non-negative, and the denominator here is positive when x is bigger than 3 and negative when x is less than 3. So clearly f of negative 1 would be negative. So f of negative 1 will give us 1 here. Negative 1 here will give us negative 4. So we get negative. F of 1 would be negative as well, and f of 4 would be positive. So we see this. So recall that 3 is where f is undefined, and also 0 is where f has value 0. So we see that f is negative from negative infinity to negative infinity to 3, and after 3 it is positive. Since the function f is defined at 0, we could actually say it's negative from negative infinity to 3, and f is positive after 3. And since we have computed these points, we can also plot them to help us with the graphing. So if you want to plot some additional points, these are, since we have already computed them, we can use them. The next thing to do is to look at the first derivative and analyze that. The first derivative, again, I'm not showing the work. If we take the derivative using the quotient rule and then simplify, then this is the derivative that we end up with. So x times x minus 6 over x minus 3 squared. Partition numbers for this would be where it is 0 or undefined. And f prime would be 0 when the numerator is 0, and the numerator is 0 when x is 0 or x is 6. And f prime is clearly undefined at 3, but remember that the function f is undefined at 3 as well. So the partition numbers would be 0, 3, and 6, and we plot them on the number line, and we now figure out the sign of f prime. And on the left side of 0, we can pick negative 1, so f prime of negative 1, so we get negative 1 here. Negative 1 here will give us negative 7. So negative 1, negative 7 would be positive here. This is a square, so that's going to be positive, so we get positive overall. So f prime of negative 1 would be positive. Between 0 and 3, we can pick 1. So f prime of 1 here, 1 here, so it's going to be negative in the numerator, so we get negative here. Notice that the denominator is always positive, so we can kind of ignore that. And f prime of 4 would be 4 times 4 minus 6, so that's negative. And f prime of 7 would be positive. So this is what we get. Again, the function is defined everywhere except for 3. So we see that it is increasing up to 0, then decreasing up to 3, and that's decreasing again up to 6, and then after 6 it's increasing. Recall that at 3 we have a vertical asymptote. Increasing from negative infinity 0 and from 6 to infinity, and it is decreasing from 0 to 3 and 3 to 6. Again, right here we shouldn't be saying that it is decreasing from 0 to 6 because the function is undefined at 3. Clearly, you might say, okay, so Okay, so let me check something here. So the function f is this. So it is defined at 0. On the left of 0, the function is increasing, and the right of 0, the function is decreasing. So we have a local max at 0. At 3, we have a vertical asymptote. Function is undefined here, so nothing here. On the right of 6, the function is defined at 6, and on the left of 6 is decreasing, on the right it's increasing, so it has a local minimum at 6. So this statement that I made here is incorrect. So we have a local max at 0 and local mean at 6. So here in blue I read I wrote there are no local extrema, but that's not correct. Okay, so now we look at the local maximum. That's okay, so I think maybe I copied from the other one and I forgot to delete this. So this would be, we have a local max at 0, and the local max would be f of 0, which would be 0, and the local minimum would be at 6, so f of 6 is 12, so that's the local minimum. The next thing to do is this. So this is our first derivative. Recall that the first derivative was this. Now if I multiply out here, I'm going to get x squared minus 6x. So that's what I did. And we have to take the derivative of this first derivative by using the quotient rule again. And if we do that and then we simplify, this is what we end up with. So the second derivative of f at x is 18 over x minus 3 cubed, which is actually simpler than the first derivative. Now we need to analyze this. So the partition numbers for this guy would be only at 3, and so clearly the numerator is always positive, and the denominator is positive when x is bigger than 3, and it's negative when x is less than 3. So clearly f double prime is positive after 3 and negative on the left side of 3. Again, we can pick 2 and 4, for example, and to see what's the sign. But if you just look at the denominator, when x is bigger than 3, x minus 3 is positive, cube of that is positive. When x is less than 3, x minus 3 would be negative, and cube of that is still negative. Okay, so we see that f is concave up from negative infinity to 3 and concave down from 3 to infinity. Again, let me remind you that we have a vertical asymptote at 3. Even though it looks like that f has an inflection point at 3, but it really doesn't, because f of 3 is undefined. All right, final step to sketch. And so we need to sketch the asymptotes. So remember, x is equal to 3 is a vertical asymptote. Y is equal to, wait a minute, I thought the oblique asymptote was x plus 3. No horizontal asymptote, so maybe I have a typo, and I can't remember which slide has the typo, but we'll see. So the first thing we need to do is draw the asymptotes and then plot the x-intercepts and the y-intercepts. And we had only one of them, and we had a local max at 0, 0 as well. We had a local minimum at x 6 and 12. And we computed a couple of points, and one of them was 416, so we're going to plot that too. So here, y is equal to x plus 3. That's the asymptote here, the oblique asymptote. So this one should be 3 here, and x is equal to 3. That's the vertical asymptote. Okay, so remember, oblique asymptote means what? It means that as x gets bigger and as x goes to infinity, the graph of the function should approach the oblique. As x goes to infinity, the graph should approach this oblique asymptote. And as x goes to negative infinity, the graph should approach the oblique asymptote as well. What else do we know? We know we knew that f is increasing up to 0 and concave down. So it is concave down and increasing up to 0. It is below the x-axis, and as x goes to infinity, it should approach the oblique asymptote. After 0, we know that it's decreasing. It's still concave down and decreasing, and because it has an asymptote at x equals to 3, so that means that it is decreasing forever, and it is getting closer and closer to the vertical asymptote. And after 3, we know that on the right side of 3, we know that it's decreasing, and it is decreasing up to 6. If you recall, it is decreasing up to 6, and it was concave up. So it is concave up, decreasing up to 6, and because it has a vertical asymptote here, the graph is going to go up forever near 3, on the right side of 3, and it's getting closer and closer to the vertical asymptote. Now after 6, it starts to increase, so it is increasing but still concave up, and it is going to get closer and closer to the oblique asymptote, because as x goes to infinity, the graph should get closer and closer to the oblique asymptote. So I hope you see what is the meaning of the oblique asymptote graphically. Okay, so this is it. So this is the end of this example. You should carefully look at each single steps and make sure that you understand this lengthy process.